operators use computerized load and trim sheets or even data link load sheets, which are abbreviated forms of the computer load sheets. Certain restrictions apply regarding last-minute changes, LMCs. Check your operator's policies. Basic or dry operating indices and weights and standard passenger weights are to be found in your operations manual approved by the authorities. Those are just examples. Did you remember that DOW and DOI data include the completely equipped airplane, standard crew with their baggage and cabin equipment, food, beverage, and water? If a weight and balance calculation has to be performed manually, this is usually carried out on load and trim sheets. An example is shown here. The left part makes up the load calculation. This is straightforward and very similar to other aircraft. It is important that you know your weight limitations covered in the limitations section. Many operators use standard weights for passengers. These weights must be stated in the operations manual. The right part of the sheet is for trim or balance calculation. It starts with the dry operating or basic index, which depends on galley equipment, number of crew members, etc. Thereafter, each moment is added graphically in the respective row. If the loaded section lays in front of the CG datum, such as load compartment 1 or passenger sections OA or OB, the index is negative. If the loaded section lies behind the CG datum, such as load compartment 4 or passenger sections 0C, 0D, or 0E, the index is positive, thus the CG travels rearwards. The fuel index may be, due to the swept wings, positive or negative. For a given fuel amount, the index is taken from this chart, which is part of the load and trim sheet. For a given weight in the cargo compartments or a given number of passengers in the cabin, a certain distance has to be traveled, left or right on the trim sheet. Here we have 1,000 kilograms loaded in compartment 1. This equals exactly 1 pitch to the left on the sheet. As you see, the pitches in the relevant sections differ. Some sections, such as OC, are very close to the CG datum, so the arm is quite short. That is the reason why a certain weight in that section has only little influence on CG movement. In other words, the moment is small. Sections at the rear or front of the aircraft have the greatest moments per weight unit, as the arm is quite long. In this example, we end up at a load index at the zero fuel weight, LIZFW, of 43 units, at a zero fuel weight of 35 tons. This is within the limit LIZFW envelope. Note that this check must be made for each calculation. Let us assume that we carry 5,000 kilograms takeoff fuel on this sector. The fuel index is plus 6.2. The fuel index of plus 6.2 is added to the index at zero fuel weight, and the resulting is the index at takeoff weight. The CG is at 38.5% SMC, or as here, MAC, for takeoff, which is within the envelope and thus within limits. The elevator trim setting for takeoff depends on the CG position and can be taken from this table for a CG of 38.5% SMC. The resulting elevator trim setting is 3.2 units. The elevator trim setting can also be read off from the trim sheet through these solid green lines, here 3.5 units. The result for our CG is as expected the same, 3.2 units. The Avro RJ has two load compartments, the front compartment 1 and the rear compartment 4. The descriptions on the following pages are for the RJ85. The compartments are of the Class D. There is no fire detection or extinguishing system. The temperatures in the compartment depend on the initial temperatures as well as the temperatures of the air supply from the cabin. Check these cargo compartment data. As you see, both compartments have very similar capacities. An important difference is the smaller rear cargo door. This might restrict package size in compartment 4. There are 3 net sections in each compartment, 11, 12, and 13 in the front, and 41, 42, and 43 in the rear. The floor is not even and not laid out as a heavy-duty version. Lashing points are available and each one can sustain an ultimate load of 1,270 kilograms. Note that the compartment doors slide inwards. Takeoff run available, TORA, is the length of runway declared as suitable for takeoff. It usually corresponds to the physical length of the runway as defined by the appropriate authorities. For normal operations, the TORA is a hard paved surface. Accelerated Stop Distance Available, ASDA, is the length of the takeoff run available, measured in the direction of takeoff, plus the length of stopway available. Takeoff distance available, TODA, is the length of the TORA measured in the direction of takeoff plus the length of any clear way. Stopway is an area beyond the runway not less in width than the width of the runway, centrally located about the extended center line of the runway and designated by the airport authorities for use in decelerating the aircraft during a rejected takeoff, capable of supporting the aircraft without inducing structural damage to the aircraft. Clearway is an area beyond the runway, not less than 500 feet wide, centrally located about the extended center line of the runway and under the control of the airport authorities. The clearway is expressed in terms of a clearway plane extending from the end of the runway with an upward slope not exceeding 1.25%, above which no objects nor any portion of the terrain protrudes except for threshold lights. A balanced field length takeoff is a takeoff with the accelerate stop distance required, ASDR, being of equal length as the takeoff distance required, TODR, or as in this chart, accelerate go distance required. In each segment, a minimum gross gradient of climb must be achieved at the scheduled weight, altitude, and temperature. The most limiting gradient will define a climb limiting or WAT weight. The limiting requirements are as follows. First segment climb. One engine inoperative configuration. Takeoff flaps gear down, power. One engine inoperative, remaining engines at takeoff thrust start altitude. Lift off point, speed, V2 gradient requirement, not less than 0.5%. Second segment climb. One engine inoperative configuration. Takeoff flaps, landing gear retracted, power. One engine inoperative, remaining engines at takeoff power. Start altitude, gear up point, speed, V2 gradient requirement, not less than 3.0%. Third segment, one engine inoperative. Configuration, flap retraction, landing gear retracted. Power, one engine inoperative, remaining engines at takeoff power. Start altitude, minimum 400 feet, may be higher due to company standard or obstacles. Speed, acceleration to final takeoff climb speed gradient requirement, none. Level acceleration is allowed. Fourth segment climb. One engine inoperative. Configuration, en route configuration. For example, flaps retracted, landing gear retracted. Power, one engine inoperative. Remaining engines at maximum continuous power. Start altitude. Third segment height. Speed, final takeoff climb speed gradient requirement, not less than 1.7%. For each takeoff, the most limiting of these requirements gives the WAT weight. Obstacle clearance requirements. During the climb through the various segments of the takeoff flight path, an aircraft must clear all obstacles by an approved vertical height, generally 35 feet, lying within a stipulated area either side of the path of the aircraft. Obstacle clearance assessment must be considered for straight-ahead climb out in a direction of the takeoff, and or a climb that at some stage incorporates a turn procedure. For a turn with a bank angle of up to 15 degrees, there is no performance penalty. For a turn with a bank angle of more than 15 degrees, the obstacle clearance height is increased to 50 feet and special procedures may be required.